In this video, I would like to explain a little bit a theory because chapter 3.1, 3.4 are using all this theorem, and it will be much easier instead of making this solving problem too long. I decided to explain the core of it separate, and then just will remind you as I solve the problem. I highly recommend to watch this video before you start working on homework, chapter 3.1, 3.4. And I broke down the video for homework into three parts, so it would be easier for you to find. So otherwise it would be video too long, and you have to rewind and forward so to find this or that problem you are interested in. So here we are going to explore the theory, how we're going to work with problems that we're going to use in our problems. So here is the thing, we are going to explore when the function is increasing, when the function is decreasing, without seeing on the graph. In algebra, we used to look at the graph and decide, right? Increasing, decreasing. Here, without seeing the graph algebraically, we're going to, not algebraically, but calculus, it's going to help us to figure out if function is increasing or decreasing, if there is a concave up, concave down, inflection points, and using second derivative, we can work with concave and find out critical points and relative maximum and minimum, or as we say, local maximum and minimum. So let's start with the first one, when function increasing. How do we find out if function increasing or decreasing? So we are given f of x. So if f prime of x is greater than 0, meaning positive, okay, then our function f of x means it's increasing. So we can figure out function increasing, decreasing using first derivative. If f prime of x is less than 0, or it's negative, obviously, hence our function f of x is decreasing. Now, what if we look at the greater than 0, less than 0? How about the case when it's 0? If f prime of x is equal 0, then our function is constant. Constant meaning it's going to go horizontally, right? Okay. There are two ways function can increase. One way is, so f increases if it increases with faster or with higher rate, or here it is, higher rate, or this one, let me draw it better. See, it's slowing down. It's increasing, but this one slope, for the second one, this one slope is much higher, right? It's a greater slope than for this one. But in both cases, first derivative is positive, And we have in both cases function is increasing, although with different rate. Okay, and the same way we can say the function will decrease two ways. Function decrease increasingly at increasing rate, where f prime of x is less than 0, and function is decreasing at decreasing rate. Okay, and f prime of x is still less than 0. And in the third case, f is constant, function is constant. When we have horizontal line, and that's where f prime is equal 0. Okay? So let's show this on the graph. For example, we have graph it's too much. Okay. And we have the following curve. Let's say it's coming like this. Let me make it much better so we can see better. So for example, let's say we have this case. So on this side, we have graph is moving up. Yes? That means our derivative is positive. Here we have graph is moving down. That means here our derivative is going to be negative. This way it's going up, so f prime of x is greater than 0, it's positive, and this one is going down, which means our derivative is going to be negative. Now, how about these points? What are these points? These points are local maximum and minimum. So when its derivative is positive, that means it's increasing, function increasing, it's positive. When when derivative, first derivative negative, that means function is decreasing, we said. And first, this one, this piece, let me see. Let me do this way so we can see better. I'll stretch like this, okay. This is much better. So here on this side we have negative, right? Because it's going down, decreasing. On this end here, we will have plus. So it's gonna be plus here, right? Because it's increasing. And then again down because it's decreasing. So how we identify these points, critical points, they represent either the local maximum or local minimum, or relative maximum, relative minimum. How we find out if it's maximum or minimum? Well, on the graph you can say that which point is max, which point is minimum. But how about in calculus when you don't have graph? So if changes from positive, see it's positive, it's moving to negative. If from positive moving to negative, that means we have here max. Here we have negative because it's down, right? From negative goes to positive. this is going to be minimum. Here we have positive this side, here it's negative. So from positive to negative, it's going to be again max. Okay, so this is the first test. So I will use it, and I'll open this testing a little bit in detail. So let's say how we find critical values here, and we test here. It's positive or negative or positive. So if it's positive to negative, that means it's going to be like maximum. Negative to positive, this is negative falling down. Positive, it's going to be minimum. Okay, so I use it in problems, so in more detail, so you will know. Okay, now let's look into details about this maximum, minimum, which represented by critical values. So when we have this, we have what? Maximum, right? Why? Because it's positive, here is negative, right? Derivative. And this represents maximum. And how about in this point? How we find out? Remember, we looked at when the derivative is 0, and it's a horizontal line, the tangent line, then derivative of x is going to be here equals 0, right? So that's how we're going to find maximum. So we will take first derivative, put it equals 0, and find the value of x. And same thing is in the case of minimum. This is going to be minimum because it's going from minimum to from negative to positive, and that represents minimum. And the tangent line is going to be also horizontal, where derivative f prime of x is going to be 0. But what if you have case like this? Okay, first of all, this type of this is a graph, but it's not a function, because function cannot have such sharp corners. Therefore, at this point, at this point, the derivative does not exist. Okay? All right. So moving on. Now let's talk about concave up, concave down. So concave up, this is what it is, how it looks like. This is concave up, okay. And this is concave down. How we find out when it's up, when it's down? So when our first derivative, let me see, I'll take this one. When our first derivative is greater than 0, meaning up, right? It's plus. And here a first derivative is negative, less than 0, which is negative. And the second derivative is going to be less than 0 or negative. And here, second derivative, it's going to be, up is going to be greater than 0, sorry. And here it's going to be less than 0. This is plus, this is minus. So this is how we're going to identify concave up or down. So we take first derivative, it's positive, second derivative, it's positive, then concave up. The first derivative negative, second derivative negative, then concave down. Now let me show you why it works the way it works. Why we say second derivative up, that's mean concave up, a second derivative negative, so concave down. Let me show you how it works. So let me take, let's say this one. Okay. So let's assume since it's symmetric, right? So let's say if this is m, slope is equal -2. So here at this point, its slope is going to be equal 0 because it's a horizontal line, right? And on this side, function is rising, slope will be +2. Now, what is happening from -2? Look, -2, 0, and 2. It's the slope is increasing, right? So if slope is increasing, hence second derivative is positive, right, or plus, that means we have concave up. This is how you can analyze like that. Let me do the same thing with concave down. Let me change this color. Okay. So let me change this color. Now, what do we have? We have here slope is what? Positive, right? It's rising. Here we have 0, right? M is equal 0. And here is coming down. M is equal -2. So we are getting 2, 0, -2. So what's happening? It's going down, right? Decreasing, which means second derivative, it's going to be less than 0 because it's decreasing. This one is increasing. This one is decreasing. Okay, so 0, less than 0, negative, and we get concave down. Okay. Now let's talk about inflection point. What is inflection point? That's a point when concavity is changing. So let's say we have something like this. So concavity is going to be somewhere here. And how we find in calculus that we have inflection point, second derivative has to be equal 0. Whenever second derivative is equal 0, then you have inflection point. But this is not enough condition. So that's the first condition. Second condition, your concavity has to change from positive to negative or from negative to positive. Let's see. We have here, this is negative concavity, right? Because it's decreasing, correct? This is negative concavity, which means second derivative is going to be less than 0 or negative. And now let's see, this one is positive concavity, correct? This piece. Because second derivative, it's going to be greater than 0. Look, the slope is dropping, is decreasing, it's negative. Here is 0, here is increasing. Here is positive, 0, and decreasing. So from the whole concavity, the green color is negative, minus, and the blue color is positive. So its second derivative has to be 0, and the one concavity has to be negative, but one sign, the other concavity another sign. Why? Because to go from minus to plus, or from plus to minus, you have to cross the 0. Yes? And that is the reason.